Please, someone's microphone is on. Keep it off. Okay, so welcome to this second session of the course Engineering Thermodynamics. In our previous session, we had discussion on introduction to the course. In this particular lecture, we will try to see some of the concepts of thermodynamics. Okay, so here we will start with the very basic fundamental concepts. Okay, so what I'll be doing, let us first try to see that thermodynamics system can be employed or can be analyzed using different ways. Okay, so whatever the thermodynamics we will be studying over here, this particular course is nothing but engineering thermodynamics. Okay, so that's why whatever the problems we will be doing, whatever the concepts we will be studying over here, these will be of nothing but engineering applications. Okay, so when we study the thermodynamics, we are having two different approaches for studying thermodynamics, that is macroscopic versus microscopic approach. Okay, so let us try to see the difference between these two approaches with the help of some illustration. So what we are having, if I say that I have some container, and inside this container, if I say that I have air filled inside it. Okay, so I am having air inside this container, and let us consider that this air is nothing but at atmospheric pressure and atmospheric temperature. Okay, so whatever our atmospheric pressure and temperature conditions are there, corresponding to that only we are having air inside this container. Okay, now what will be happening when we are having air inside this container? Obviously, we will be having a number of air molecules over here. So we know that at the molecular level, if we try to see, every substance will be having number of molecules. Okay, and we will be finding that these molecules will be interacting with each other. So these molecules will be having some random motions, they will be having some vibrations, oscillations, etc. Okay, and they will be having some collisions in between them. So as a whole, if you see, we are not having any medium which is actually perfectly continuous if we see at the microscopic level, okay, or molecular level. So what we will be having, we will be having some molecules, some space where actually molecules are located, and we will be having some area in between the molecules. That area will be nothing but a void space. Okay, so that will be some empty area if we see at the molecular level. Okay, so now if we have to define the property of this type of thermodynamic systems, what we have to do, we have to first understand the behavior of individual molecules, and then we have to do some sort of averaging in order to perceive any property at the macroscopic level. Okay, so this is like what happens in case of the situation when we are studying the system from the molecular point of view. Okay, so basically what we are having number of molecules, and we are having some void spaces in between the molecules. It means system is not a perfect continuum. Okay, so under this situation, if we are studying the system by considering the behavior of each and every molecule, that type of system is particularly considered as we are studying that system from the microscopic point of view or molecular point of view. Okay, now let us consider that whatever the container I have taken, let us consider that size of this container is nothing but equal to 25 mm. Okay. So now we will try to find out that how many number of molecules will be there inside this container. Okay. So what will be happening? We know that 1 mole is nothing but equal to 6.023 into 10 to power 23 molecules. That is something which we already know. Okay. Now we also know that for a gas, 1 mole is nothing but equal to 22.4 liters. It means 22.4 liters of a gas will be equal to 6.023 into 10 to power 23 molecules. Okay. Now, what we have to do, we have to identify that how much volume we are having. So, whatever the volume I have considered, if I consider that I have a cube, okay, of 25 mm side, and this cube is actually entirely filled with the gas. So, in that case, my volume of the container will be nothing but equal to 25 cube, and this volume we are calculating in mm cube. Okay, because we are having the side of this container as nothing but in 25 mm. So now what will be happening in this particular situation, if we just try to find out corresponding to, for 22.4 liters of gas, we are having 6.023 into 10 to power 23 molecules. Now we can calculate for 1 liter of gas, and this much millimeter cube, I can convert this into corresponding liters, and I can determine that how many number of molecules we will be having. So if you try to do so, you will be finding that corresponding to 25 meter cube 25 cube cube, we will be having nothing but around, if I write in terms of order, we will be having something around 10 to power 20 molecules within our system. Okay. So now you can think of 25 mm is a very, very small sized container. 25 mm is nothing but equal to 2.5 centimeter. Okay. So if we are having a cube with side of 2.5 centimeter, what we are having within that cube, if we are considering that some gas is filled, what we are having nothing but something around close to 10 to power 20 molecules of gas inside that container. Okay. So this is like you can see from here. Now what will be happening if we are having a single molecule? If I have to specify its location in the space. Okay. So in order to specify the location of a single molecule in space, what we have to do? We have to nothing but specify its 3 coordinates. Okay. So obviously, if I say I have XYZ coordinate system, so if I take a single molecule, so for that particular molecule, I have to specify its coordinate positions X, Y, and Z at any particular instant. Okay. Apart from that, as I have already told you, at the molecular level, molecules will be having different kinds of motion. So because of that, what will be happening? We also need to know the velocities of molecules. Ux is velocity in x direction, Uy is velocity in y direction, and Uz is nothing but velocity in z direction. Okay. So it means if we study a system from the molecular perspective, what I have to do, whatever the number of molecules we are having within our system, for each molecule, what we have to do, we should know about its X, Y, and Z position. And at the same point of time, we should also know about its velocities, Ux, Uy, and Uz. Okay. So it means for a single molecule, nothing but we are having 6 different characteristics. So we require 6 equations in order to determine its motion. Okay. So likewise, what we are having nothing but 10 to power 20 molecules within a cube of 25 mm side. So what will be happening? We have to determine how many number of equations? 6 times 10 to power 20. So it means these many equations we have to solve if we are having only a very, very small system with 25 side where gas is filled inside this container. Okay. So it means that if we are studying our system from the molecular perspective, we will be having nothing but what we will be having? We will be having nothing but requirement of solving 6 equations for each molecules, and as for engineering applications, our length scales are very large in comparison to the molecular dimensions. So that's why we have to go for very large number of molecules. So whatever the number of equations we will be getting, that will be not possible to solve even with the high ending computing, whatever we are doing. Okay. So it's like yeah, Vaibhav, please. Vaibhav, please mute yourself. Okay, so what will be happening? We will be having a large number of equations. Okay, now what we want to do, particularly when we are doing the engineering applications, so even with the high-end computing workstations, whatever we are having in the present days, with that also we cannot go for these many equations. Okay, so that's why what we will be doing over here, we can club a number of molecules. So another strategy could be that we are having large number of molecules. So what we are doing, the first way was that we can study the individual molecular motion, but that will be applicable only if our system size is of the molecular scale. Another strategy could be what we can do, we can combine a group of molecules. Okay, and these group of molecules we can call nothing but some particles. So what we will be doing at each and every location, we will be considering a group of molecules, and these group of molecules will be nothing but considered as parcels or particles. Okay, now what we can do, then we can analyze the motion of these individual particles, and then with the help of statistical averaging. So what we can do, statistical averaging we can employ, and with the help of statistical averaging we can actually determine the averaged properties or bulk properties of the system. Okay, so another approach is that we are nothing but converting the group of molecules, we are considering these group of molecules as nothing but particles. Okay, and then these individual particles we are analyzing, and then finally we are taking statistical averaging in order to determine the bulk properties. Okay, so this type of approach nothing but employs kinetic theory of gases. So you might have already known in your fundamental subjects that we are having the we can analyze the system with the help of kinetic theory of gases also. So kinetic theory of gases basically employs this approach where we take a group of molecules as parcels, and then we try to do the statistical averaging in order to determine the bulk properties. Okay, so this type of thermodynamics, which studies the behavior of our system from the molecular perspective, or I should say from the perspective of the statistical averaging, that particular thermodynamics is known as classical thermodynamics. Sorry, that is known as statistical thermodynamics. Okay, so here we are trying to study our system from the molecular perspective or from the statistical averaging point of view. That particular thermodynamics is something which is known as statistical thermodynamics, and it is not mainly required for engineering applications, because in engineering applications what we are having size of system very large in comparison to the molecular dynamics of the system. Okay, so now let us try to see the molecular approach. So in case of molecular approach, in case of engineering systems, what we are having nothing but macroscopic approach. So in case of macroscopic approach, what we will be doing, we will be having some system, as I have already told you, that we are having, say, 25 side cube. So inside that we are having some medium, say nothing but our air. So in case of macroscopic approach, what we will be doing, we will not go into the molecular details of this gaseous medium. Rather, what we will try to do, we will try to perceive the bulk properties, whatever we are getting from this particular system. Okay, so obviously we know that if we are having some gas inside the container, so what will be happening? That gas will be having certain pressure. Okay, and moreover, if we are having our scales in the engineering order, so in that case we will be finding that almost at each and every location within this system, whether I go to this particular corner, that corner, this corner, or any other area within the bulk, I'll be finding that whatever my bulk properties are there. For example, bulk properties, I refer to the pressure and temperature of the system. So if I talk about bulk properties of the system, I'll be finding that pressure at this particular location, say if it is P1, here also it will be P1, here also it will be P1, here also it will be P1. So similar will be applicable for other properties also. Okay, so when we talk about macroscopic approach, here what we do, we don't go into the molecular details of the medium or the system. Rather what we do, we try to perceive the bulk properties of the medium. Okay, so while we are considering only the bulk properties into consideration, by considering that our medium is nothing but completely homogeneous. Okay, so while we are seeing that everywhere we are having same pressure, same temperature, it means we are not considering the void space in between the molecules. Okay, so here what we do, we will not consider void space between molecules. Okay, so this is like one important point over here in the microscopic approach. In the microscopic approach, we consider that whatever medium we are having under observation, that medium is nothing but completely homogeneous. Okay, and we don't consider the void space between the molecules which we are having under consideration. Okay, so we consider that everywhere we are having nothing but continuous medium. Okay, so everywhere we are having nothing but continuous medium. So in macroscopic approach, whenever we analyze the system, so that particular subject of thermodynamics is something which is known as classical thermodynamics. Okay, so this particular subject, whatever we will be studying, where we will be analyzing our engineering systems from the macroscopic point of view, this particular subject is nothing but our classical thermodynamics. Okay, now what will be happening? Let us try to see that we have taken this assumption of continuum. Okay, so we have taken an assumption that our medium is continuous. It means we are considering the assumption of continuum. So let us try to see under what assumptions this condition of continuum actually satisfies. So for that, first we will be defining our first parameter as length scale. So let us consider that L is nothing but our characteristic length of the engineering system, whatever we are having, and let us consider that our lambda is nothing but mean free path. Okay, so you all know what is mean free path. Mean free path is nothing but the average distance between the successive molecular collisions. Okay, so what we are trying to do over here, we are trying to study the concept of continuum, and we will try to see that what are the conditions under which the assumption of continuum is actually valid. So lambda is something which is known as the mean free path, and L is characteristic length. So if value of L is very large in comparison to lambda, it means if our length scale of the system is very large in comparison to the molecular motions, under such situation we can say that our assumption of continuum is actually valid. Okay, so this particular criteria of length scale is basically characterized with the help of one non-dimensional number. That particular non-dimensional number is referred to as Knudsen number. It is given by symbol Kn. It is nothing but equal to L by lambda. Okay, so if the value of this L by lambda is sorry, I have written it wrongly. So this Knudsen number is nothing but represented as lambda by L. Okay, so it is represented as lambda by L. If value of this lambda by L is less in comparison to 0.01, under this assumption we can consider 0.001, under this assumption we can consider that our medium is nothing but continuous. Okay, so that is the quantification under what assumption we can consider that our medium is behaving like a continuous medium. Second criteria comes of time scale. Okay, so generally what happens when these molecular motions takes place, so molecular motions are having very small time scale of the order of femtoseconds or nanoseconds. Okay, so molecular activities happens in very small time interval, which is of the order of nanoseconds. However, when we talk about our engineering phenomenon, so in engineering phenomenon, we will be mainly concerned within the scale of seconds, or hardly we will go to milliseconds. Okay, so from there you can see that while the molecular motions will be happening at the nanoseconds, and whatever the phenomenon which we will be able to observe in the engineering scale, that will be nothing but happening in seconds or milliseconds. Okay, so because of that, what will be happening, particularly at the engineering scale, whatever phenomenon we will be observing, that phenomenon will be giving us nothing but time averaged bulk properties. Okay, so what will be happening? Already whatever the molecular motions are happening, their time averaging is actually done over that large scale, because our scale is very large, at which we can see that molecular activities has already happened, and these are nothing but giving rise to something like time averaged bulk properties. Okay, so these are the two very important conditions under which we say that if these conditions are being satisfied, then we say that our situation of continuum or assumption of continuum is actually valid for the engineering applications. Okay, so this is what we will be doing throughout our this particular course, because here our all the applications are of nothing but engineering length scale and engineering time scale. So because of that, we will try to analyze all our systems under the assumption of continuum. Okay, and we will try to study our systems from the concepts of classical thermodynamics. Okay, now let us try to go little bit more details of the subject. So let us define what is a thermodynamic system. Okay, so our next concept is nothing but a thermodynamic system. Okay, so a thermodynamic system is nothing but any device, or I should say the combination of devices. Okay, so if I take any device or combination of devices that represents some quantity of matter under observation. So that particular entity is something which is called as nothing but our thermodynamic system. Okay, so for example, we start with our very fundamental example. So let us consider that if you are boiling or heating water in container, so you are having some water. Okay, so let us consider initially the temperature of water was nothing but 25 degrees Celsius. So now what you are doing, say you have put this container on some stove. So from the stove you will be getting some flame will be coming, and this flame will be nothing but it will be actually heating our container. Okay, so if this flame is hitting our container, so what will be happening? Whatever the fluid we are having inside, its temperature will increase. Okay, so if you just record with time, so you will be finding that at some point temperature will go to 30 degrees Celsius, it may go to 35 degrees Celsius. So as long as you are providing the heat. Okay, now let us consider that you want to study or analyze the behavior of this particular system. So if you want to analyze the behavior of this particular system, what you can do, you can consider. So now my understanding is that only I want to analyze whatever the liquid medium I am having inside the container. Okay, so for that only I want to analyze the water portion. So what I will be doing, I will be actually creating some arbitrary control volume, which will be nothing but surrounding only the periphery of this liquid which I want to study. Okay, so that particular boundary will nothing but represent as our system. Okay, so this is the overall idea, that anything which we are having under observation, that particular thing we call as nothing but our system. Okay, and anything which is outside this system, that is something which is known as the surroundings to this system. Okay, so anything which is outside, that we call as nothing but the surroundings to this system. Okay, and what we are having one boundary in between the system and surrounding. So this particular boundary we call as boundary only. So the demarcation in between the system and surrounding is represented by one hypothetical boundary, so that we call as boundary, and this particular boundary need not to be a real surface. Okay, so it can be imaginary. For example, if I take the example of this container, so for this particular container, you can see that our idea was only to study the behavior of water. So that's why what we have considered, these three boundaries, whatever we have considered, these three boundaries are nothing but physical boundaries, real surfaces, which are nothing but the internal face of the container. Okay, internal surface of the container. However, for the top, because from the top side, this container was open. So while we are studying this water as our system, what I have done from the top also, I have created some boundary. Okay, some surface which is actually specifying the demarcation in between our system and surrounding. Okay, so here you can see that for this particular system, these three faces, this one, and this one. These three faces are nothing but represents the real boundary, whereas this particular surface, whatever top boundary I have taken, this is nothing but my imaginary boundary. Okay, so from this we can make one conclusion that boundary need not to be a real surface. We can have both real as well as the imaginary boundary. Okay, and in a single system also we may have both real as well as imaginary. So another important thing is that while we are considering the boundary, this particular boundary do not have any thickness. So this is of nothing but zero thickness, and it doesn't occupy any area or volume of the space. The only idea of specifying the boundary is to demarcate in between system and surrounding. Okay, because we cannot analyze our entire thing as our system. So whatever the thing we want to study, that particular thing we call as our system, and anything which is outside our observation area, that we call as surrounding, and whatever the transition we are having or demarcation we are having in between our system and surroundings, that particular demarcation we call as nothing but our boundary. So boundary is nothing but a it may be real or it may be imaginary. Okay, and boundary is having zero thickness. Now, if we specifically go into more details, we can specify the first type of system as nothing but our closed system. It is also known as control mass system. It is also known as fixed mass system. Okay, so there are three different names: closed system, control mass system, or fixed mass system. Okay, so if we are having a system like I have told you in the previous example, that I have something like this container, and inside this container I have nothing but water. Okay, and from the bottom I am adding certain heat over here. So I have some gas stove. Okay, and what I will be doing, I am considering this as nothing but my system. So now for this particular system, you can see that this boundary is completely closed from all the sides, and only because of this particular burner, whatever we are having over here, because of this we are only adding the heat into the system. Okay, so we are nothing but adding energy across the boundary of the system, and within this system, whatever the amount of water we are having, actually that is fixed. That amount of water is actually not changing. Okay, so here what is basically happening, there is no mass transfer across the system boundary. So if we are not having any mass which is transferring across the system boundary, in that case what will be happening, we will be having within our system, our mass will be remaining always fixed. So we will be having fixed mass inside. So that's why this particular type of system, where we are having only energy interaction across the boundary, and we are not having any mass transfer across the boundary, and mass of the system remains fixed, that particular type of system we call as nothing but our closed system, control mass system, or fixed mass system. Okay. Now another type of system where we are having the interaction of mass as well as of energy, that particular system we call as nothing but our open system or control volume. Okay, so now let us take the example of our electrical geyser. Okay, so what happens in case of geyser? In case of our electrical geyser, we are nothing but having some boundary, and in this boundary, what we have some inflow pipe and we have some outflow pipe. Okay, so what happens in our geyser? In our geyser, we are having actually flow of water. So from here water will be coming inside, and inside we will be having some heating element. So this heating element will be actually adding some heat to our system. Okay, so if I consider that water is my system, so what I will be doing, I will be creating my system boundary, something like this. So now this black dot line is nothing but represents my system boundary. So here what will be happening in this system, across the boundary of the system, this water is actually coming inside. Okay, and from here also some water is going out. So at this particular point we are having nothing but inlet, where through this inlet we are having inflow of the medium. Okay, and here we are having nothing but outflow of the matter. So because of that, what will be happening across the system boundary, if we see, some amount is entering into the system, some mass is entering into the system, and some mass is actually going out of the system. So any system where we are having both interaction of both mass as well as energy across the system boundary, in that case we will be calling that type of system as nothing but our open system or control volume. Okay, so why we call this control volume? Because if you see this typical example, so in this typical example what has happened, we are having this type of arrangement. Okay, so here you can see that here then we are having water, everywhere water we are having. Okay, and then we have taken some fixed boundary. Okay, now if you see the boundary of the system, whatever we have considered, that is fixed. So it means it is nothing but volume of this boundary is not changing. So that's why we are calling it as nothing but control volume. Okay, but whatever this boundary of this control volume we are having, that is something which is called as control surface. But what we are having across this control surface, we are having inflow and outflow. So it means we are having the interaction of mass as well as interaction of energy. So that's why we call this type of system as nothing but our open system or control volume. Okay. Then another type of system, third type of system we are having, which is particularly known as isolated system. So what we do in case of isolated system, whatever we are considering here, we will not be having any mass interaction. So mass interaction, we are not having any. So we have no mass interaction, and at the same point of time we have no energy interaction. Neither we have mass interaction nor we have energy interaction. So isolated system is a kind of system which is actually not interacting with its surroundings. It is not having any mass and energy interaction. So it's very, very difficult to obtain the isolated systems because these are very, very idealized systems. Okay, so normally isolated systems are very, very difficult to achieve in reality, because in reality we will be finding that always there will be interaction of the system with its surrounding. Okay, now one more important concept we will try to see over here with the help of another example. As I have already told you that boundary we are having is nothing but some hypothetical area. Okay, so we may have a system of fixed or variable boundary. So then let us try to see with the help of an example that what kind of system will be of fixed boundary and what will be of variable boundary. So let us consider a piston cylinder device. So say this is our cylinder, and inside this cylinder we are having nothing but a piston. Okay, and inside this piston and cylinder, let us consider we are having some gaseous medium, and say this is our system. Now what I have done, I have fitted some additional arrangement over here in order to keep this piston at the fixed position. Okay, so here what will be happening, even if I add some heat to this gaseous medium, so even if I add some heat to this gaseous medium, irrespective of that, what will be happening, because we have this piston which is constrained inside this cylinder, so this piston cannot move. So because of that, what will be happening, irrespective of addition of heat, this boundary of the system will be actually remaining fixed. So this is nothing but example of a fixed boundary system. Another example we can consider a similar system, and in this similar system, what we are doing now, this is our initial boundary of the system, and now we are adding a certain amount of heat. Okay, so now because of the heat, what will be happening, this gas will be expanding, and because of the expansion of the gas, we will be finding that after some time, so here what we will be having, initially we will be having some fixed boundary, and after some time, while we will be adding the heat, this piston will be going to some new position. Okay, so because piston will be expanding with time, so gas will be expanding with time, so that's why piston will move in upward direction. So after some duration, piston will be shifted slightly upward. So because of that, my new system boundary will be something like this. Okay, so it means this is nothing but example of an variable boundary system. So another characteristic of the boundary is that boundary of a system can be fixed or boundary of a system can be variable. Okay, so now what I will do, I will stop at this point, and whatever the your doubts you are having from this lecture as well as from your previous lecture, that particularly you can type in the Excel sheet whatever I have shared with you, and today we will be having that doubt clearing session from 2 to 3. Okay, and our remaining concepts, particularly on the discussion of states and properties, we will be starting in our next lecture.